All right, finding the equation of the tangent line, which we've done before, only this time we're using implicit differentiation. So obviously the technique's going to be pretty similar. We're going to use point-slope form just like last time. The big difference is that we're going to use implicit differentiation to find that derivative. Now, if you haven't watched any of this tangent line stuff before, I've got a very aptly named chapter prior to this in calculus called something like Finding Tangent Lines or something. And that's going to walk you through, reminding you what point-slope form is, and showing you, given the derivative, how do you find the equation of the tangent line. Now in this video, we're obviously going to take that one step further and actually find the derivatives using implicit differentiation. All right, so even if you didn't want to use implicit differentiation, pretty much you're going to have to on this particular problem, right? Because we've got a y kind of buried in amongst stuff. So when in doubt, use implicit differentiation in that situation. What to do? Well, so they say find the tangent line. So we have a point, and in these type of problems, they pretty much always give you a point. And the only thing we don't have is slope, right? Because to use point-slope form of a line, we have to have m. We have to have the slope. And that's going to come from the derivative. So this will happen a lot in calculus, is they'll want you to find tangent lines sometimes. And the key is always going to be find a point, figure out what the slope is at that point, and then just plug and chug through the point-slope form. At that point, it becomes an Algebra 1 problem. So the key here is just to find the slope, but of course the slope is just going to be the derivative. If you plug 3, 4 into the derivative, you'll get the slope at that particular point. All right, so take the derivative using implicit differentiation. So we got x equals this junk. So how do I take the derivative? Well, first of all, I want to rewrite this as a power problem. So 25 minus y squared to the 1/2 power. Take the derivative of both sides. Derivative of x is just 1. Derivative of the right side is 1/2 times 25 minus y squared. This is a chain rule problem. So new power is 1/2 minus the minus 1, so negative 1/2. But then the derivative of the inside, our u prime from the chain rule, is going to be negative 2y times y prime. And that y prime is the thing that's easy for to get, but obviously super important because we're trying to find y prime. When I want a derivative to plug this point into to get the slope of my line, I'm plugging into the derivative, which is called y prime. F prime dy dx, y prime, all these things are the same thing. They're just the derivative of y. So at this point, I've got to just, if I want to find y prime, I just need to get it by itself. So right now it's over here buried amongst all this junk. I just need to bring it to the forefront. So this negative 2 cancels the 1/2 and just leaves a negative. I just moved this negative sign out front where I wouldn't forget about it. So I've got a 1. And then I've got to divide by everything except the y prime. So I've got to divide by a negative 1 by a negative y times 25 minus y squared to negative 1/2. So that is going to be, and divide the other side by the same thing. So I get 1 over negative y times 25 minus y squared to negative 1/2. And all that is equal to the only thing that's on the right side anymore, which is y prime. Now this thing right here, that's a negative exponent, which means I can just move it upstairs and it becomes positive. So, and it's a square root, so I'm going to get square root of 25 minus y squared all over negative y equals y prime. All right, so I'm pretty sure that's the correct derivative. Let's see what happens. I've got a point 3, 4 that I can plug in. You'll notice I don't actually need x. All I need is y. Because if you look at my equation now for the derivative, there's only y's in there, but that's fine. So y prime of 3, 4 is just going to equal plug in 4, because 4 is the y term, the y number. So it's going to plug that 4 into wherever I see a y. So that's going to be square root of 25 minus 16, it's 4 squared of 16, all over a negative y, so negative 4. Which gives us, let's see, 25 minus 16 is 9, square root of that is 3, so negative 3/4. All right, crazy. So now my slope, my y prime of 3 comma 4, whatever, is negative 3/4. And that is awesome, because now I have the slope and I have the point. All I have to do is plug and chug into the point slope form. Now if you want to use slope intercept, you're welcome to do that. I would highly recommend, and I advocate this in the previous chapter about tangent lines, just get used to using point slope because it's so much faster. Check out how fast this is. Y minus the y coordinate is 4. I'll just rewrite it up here for you if you're not familiar. Y minus y1 equals m times x minus x1, where this x1 and y1 are just the x and y coordinates of the point we know, and then m is just slope. So that's why I'm plugging in. So it's y minus this 4 equals the slope I just got, which is negative 3/4, times x minus the x coordinate, which is 3. And I'm done. You could rearrange this into slope intercept if you wanted. Just distribute the negative 3/4, and you get some fractions that might be a little bit painful. But hey, that's easier than solving for a b, which you'd have to do in slope intercept form. And also, for 90% of teachers, it's fine. Just write this down and move on. You don't need to rearrange this in the slope intercept form. Point slope form is a totally legit style of line, So it's so fast. Just plug in the slope, plug in the point, get on to the next problem. That's what it's all about, is finishing the test. That's your first priority. Getting the right answers, fully simplifying, getting stuff in the right form. That's all just like little shades of gray. You got to finish the test first before you can start worrying about the icing on top. All right, tangent line example. Once again, we're looking at something funky here. I have no idea what this graph is. That last one was actually a circle, but I have no idea what this one is. Doesn't matter though, because we can just use implicit differentiation. Once again, they gave me a point, so I just have to find my m. That's all I need. All right, so to find slope, again, just find y prime, or the derivative, and you're all set. So derivative of this, derivative of y, I'll just differentiate everything here. So we got y prime. It'd be tempting to put 1, but it's actually y prime. Derivative of 3 is just nothing, so 0, equals 2x minus 2y y prime. So now remember, because I had 2 y terms, I had one here and one here in the original, that means I'm going to have y prime show up twice. It's really important that you got a y prime for every y, otherwise you'll get it wrong. All right, so now the trick is going to be to get all my y terms on the left, all my non-y terms on the right, and solve for y prime. So I'm just going to add this to both sides, 2y y prime. So on the left now I'm going to have y prime plus 2y y prime equals 2x. I want to get my y primes isolated, so what I do is I factor out y prime, which will give me, that first term is just a y prime, so it just leaves a 1 behind. And then a 2y y prime just leaves a 2y. And finally, divide by 1 plus 2y to get that y prime on its own. So I get y prime equals 2x over 1 plus 2y. All right, excellent news. Am I done? No, because this was just a means to an end. All I did that for was to find the derivative so I can plug in this crazy point and get the slope I want. So right now I need to find y prime of the point 3 comma 2. And you'll notice that instead of just doing y prime of a number, I've got 3 comma 2. And that's because my derivative can have both x's and y's in it. In this case, sure enough, it does. So it's kind of wacky that when you plug into something like this, you've actually got x's and y's to plug in. So just be really careful. It's 2 times x, which is 3, but then that's 1 plus 2 times y, which is 2. So it's kind of cool that we're plugging in 2 different letters at the same time. So that's just 6 over 5. All right, so my slope is 6/5. No need to convert that to anything. Point slope forming will be done. Y minus 2 equals 6/5 times x minus 3. And voila. There she goes. All right, so as you can see, you're going to have to use the implicit differentiation technique to find y prime, but once you got that, just plug and chug right through it. All right, find the line tangent to this piece of junk at 0, 0. Well, gee, doesn't this look like all the other ones we've done? We have a point, we just need a slope. It's pretty much how these always work, so excellent. Now, there is one other type of problem that I covered really well in that previous tangent line example, tangent line chapter, that I mentioned a few chapters before this one. We've got the chapter full of videos about how to find the tangent line equations. I cover that pretty well. Every once in a while I get something wacky, like find the equation of the line tangent to this function that's parallel to some other line. But that's just kind of some trickery. It sort of works backwards, but you should watch that video if you have that type of problem to work on. But most of them are like this one I've got here, where we just want to find the derivative, they give us a point, and we just plug and chug through it. All right, so step number one, we always take the derivative. So what is the derivative of sine of x plus y? Well, it's going to be a chain rule problem. So derivative of sine is cosine of the same thing, so x plus y. But now I got to multiply by u prime, which is the derivative of x plus y. And that's going to be the derivative of x, which is 1, plus the derivative of y, which is y prime. And the derivative of x is just 1. Now if I had forgotten this y prime, at this point there wouldn't be any y primes at all in the problem. So keep that in mind. That's a way to spot when things have gone wrong. So now this is kind of a little bit interesting one algebraically. We've got a 1 plus y prime. I want to get y prime by itself. Can I do that now? I think I can. If I divide both sides by cosine of x plus y, that cancels that. So that just leaves me with 1 plus y prime equals 1 over cosine of x plus y. So that seems reasonable, right? And then to get y prime by itself, I just subtract 1. So just get rid of this, put a minus 1 over there, and we should be set. All right, so y prime equals all that junk. Great. Doesn't mean I'm done with the problem. Just means I have something to plug my point into to get some slope action. So m is going to equal, let's see, y prime of the point, which in this case is the origin, 0, 0. That's going to be 1 over the cosine of 0, because 0 plus 0 is 0, minus 1. Now this is, every once in a while in calculus, you're going to need to know your unit circle a little bit. What's the cosine of 0? Now let's see, 0 is straight to the right on the unit circle. It's 1. So 1 over 1 is just 1, minus 1 equals 0. Fantastic, very fun. So m equals 0. All right, this is going to be a really boring equation, isn't it? Because we're going to get y minus the y coordinate, which is 0, equals the slope, which is 0, times x minus the x coordinate, which is 0. Wow. So a lot of stuff cancels here. 0 times all that is just 0, so we get y equals 0. All right, did something go wrong? Is this a legal answer, or is this undefined, or some crazy singularity in the universe? It's just a horizontal line, isn't it? Because I've got a letter. If I'd gotten 0 equals 0, then we'd have a problem. But y equals 0 is just a horizontal line at the x-axis. So it's just the x-axis itself, basically. So whatever, I have no idea what this graph looks like, but it seems that right here, it goes through the origin, and it's going sideways at that instant. It doesn't mean it kicks off forever. It could go shoot up like that, or woo, who knows. These things can be wacky shapes, but the point is, right there, its tangent line is a horizontal line that's just the x-axis. All right, so that is it for finding tangent lines using implicit differentiation. Pretty complicated, pretty annoying, but you just gotta really, really, really be careful. For every y that's in the original problem, you're gonna get a y prime out of it. And that is the mistake you don't wanna make with implicit differentiation.